Okay, good morning, my dear students. To give a proper idea of this diffraction, I just happen to make this video. Okay, let us see very briefly, okay, about this diffraction of light. Actually, if you have an obstacle means just like any substance which block the light, okay. Then you happen to take a light source, as is the light source. Then if you pass light in this way, as we know, light travel along a straight line, so there should be image formed here. And actually what this image is nothing but the shadow. This should be the shadow. This is the shadow portion. And if light happen to travel along a straight line, the shadow should be perfectly dark here. This should be perfectly dark shadow. But we know that whenever an object casts shadow, or whenever an object is making a shadow, the shadow is never perfectly dark here. Still some light is present in the shadow region. So it shows that light actually it bends around the corner of the obstacle here. Something like bending here. So light is found to be present here. It means the shadow is not perfectly dark. Okay, so this phenomenon in which light bends around the corner of the obstacle is what we call as a diffraction of light. So to summarize, let me write very briefly here. Phenomenon in which light bends around the corner of obstacle. This is we call as a diffraction. Okay, and in diffraction we have two types of diffraction. One is the Fresnel diffraction here. There are two types. The first one is the Fresnel diffraction, and the second one is the Fraunhofer diffraction. So in the syllabus, the second one is included, and the main difference between the two is that in Fraunhofer diffraction, distance between the source and the screen. This is the screen. The distance between the source and the screen is infinite here. So in Fraunhofer diffraction, distance between source and the screen is infinite, whereas in Fresnel diffraction, the distance between source and the screen is finite. Finite means you can have a certain distance, maybe like 1 meter, 2 meter like that. Okay, so this is the main difference between Fresnel and Fraunhofer diffraction. Okay, next, after we know briefly about this, we'll be talking about this width of central maximum here. Okay, now just to get the derivation of this width of central maximum, let us draw one diagram. So suppose here is the slit, and you have the source of light as the source of light. Then you take a lens, it's a convex lens, all right, source, and this is the midline, and let this be the screen here. This is the slit, opening is there. Then you take the ray of light coming from the source, let this be the ray of light, and after it passes through the first lens L1, the ray travels straight like this, almost a parallel line. Then this has to pass through another lens we call it as a L2. The second lens is L2 here. Then the rays will be converged here. Okay, and this point is the central point here. That will be the point, the midline, along this midline here. Then I'm going to choose a point P here, somewhere P. Okay, then say the same ray has to be focused here at the point P. Then we're going to have another line, seems to be coming out from here, and this is the separation or opening. Wide of the opening is what? D. This is what we call as the width of the slit. This is the width of the slit. Then if this point O is shifted to P, then we can imagine another figure similar to the first one, like this, and they are meeting at the point P one more time here. Okay. Then here we have a small triangle, and this angle displacement will be theta. So this is theta, this is also theta. So similarly, this angle should be theta here. And this distance, the short distance, is what we call as the path difference. This is what delta x. So delta x represents the path difference here. Okay. Now, after this, let us name this distance OP as x or something here. X. And on the screen, if you look on the screen, this is the midline. And you're going to get a variation in the intensity of light, like this. Here. So this is the central maximum. We call it central maximum, and this point P, imagine it here, right now here. So this distance should be x. On the other side also, the same distance x should be available here, xx. Okay, and this distance here, this is what we call is the weight of central maximum. Let's write W here. So this is the weight of central maximum. Okay. To derive the equation for the weight of the central maximum, first we need to know that weight of central maximum, this is the central maximum, this is equal to x plus x, which is equal to what? Twice x here. So if you can get the value of x, you can put here, and y you can get the weight of central maximum. So now I'm going to tell you how to find the value of x. Okay, we'll be referring the figure one more time. Okay. Then here, coming to the figure again, we have got a triangle here. So you name this triangle as M, for example. So in the triangle MPO, you can see, if you apply tan of theta, this is going to be perpendicular by base here. So perpendicular will be OP. Okay, so in this triangle here, I'm talking about this MPO here. So perpendicular is X, and the base will be MO. And the distance between the slit and the screen, you give it as D, for example. So perpendicular by base, the base should be now D. So you can write it as D here. So we call equation number 1. Okay, and you have got another triangle here, the smaller one here. This small triangle, this is the 90 degree. and you know the hypotenuse is D here. This is the perpendicular, and this is the base. So if I apply in the smaller triangle again here, so let me call this A, B, and C here. So in triangle ABC, if you apply sine theta will be equal to, perpendicular will be this one BC, this is what delta x, and the hypotenuse will be, the longest side is what, AB, which is equal to what, D here. Okay, so equal to equation number 2 here. Then as this angles theta, this theta is small, this has to be noted here, as theta is small, tan theta will be taken as equivalent to sine of theta here. Therefore these two equations will be the same, so you can write delta x by D is equal to x by D here. So this will give you part difference, delta x is equal to x D by D here. You can call it equation number 3. Okay, then we'll come to the figure again. We have taken this point P to be the minimum. This is the minimum point, and this is the maximum. All the peaks are maximum here. This is maximum, this is what, maximum here, and these are the minimum here. So this is your first minima. Okay, so this is second minima, third minima, like that. So this is, I say again, this is the first minima. So for first minima, the part difference, this delta is the part difference, the part difference must be equal to an integral multiple of wavelength here, where n is the integer, like 1, 2, 3 here. Okay, lambda is the wavelength of the light source. This source is having a wavelength lambda here. Okay, so this condition must be satisfied if you take the minimum point, the first point. And I took this equation because this point P lies at the minimum here. And if it is first minima, you have to put n is equal to 1, second minima n is equal to 2, like that. Okay, so for first minima n is equal to 1, so we can write delta x is equal to what, lambda. So now put back here, therefore delta x will be written as lambda is equal to x D by D. So this will give you x D is equal to lambda D, or finally x is equal to lambda D by D here. Therefore width of, or the width of central maximum now becomes twice x, I told you. So now 2 into x is what, lambda D by D. Therefore the final width is twice lambda D by D here. Okay, this is the equation.